Okay, we're ready to begin the afternoon session. Our apologies for being a few minutes late. We're going to start off with Alex Shibakov talking about countably compact and pre-compact sequential groups.
It's really nice to be invited to the conference. I had the fortune and the privilege of being Gary's graduate student, and I owe a large portion of whatever little I know about topology to Gary, and even though he will deny it, I owe him my life too. So I'll talk about countably compact and pre-compact sequential groups, and there'll be a few theorems that give positive results, but mostly it's about counterexamples with pathologies. So we'll start with a theorem that shows why countably compact is of particular interest rather than something stronger that is compact. And this theorem has been mentioned before. So every compact countably tight group is metrizable, and therefore, since sequential spaces are countably tight, there are no interesting countably compact. There are no interesting sequential compact groups. So we have to shift our focus to countably compact or some other variation of compactness. So here's the definition of sequential. Of course, everybody has seen it several times, but just to remind you, basically sequential spaces are those where topology is described by convergence. Not directly, as in the case of Fréchet spaces, but indirectly. You can recognize whether the set is closed or unclosed by just looking at convergent sequences. So here's the class of slightly more manageable convergent spaces that I mentioned. Fréchet, that's where the closure operator is directly described in terms of convergent sequences. And the first result that probably everybody starts with is that if you take a sigma product of Z2s, or in other variations, it's unit circles, or whatever your current flavor of compact group is. I'll use Z2 because most of these groups can be Boolean. Then the sigma product of omega-1 copies of Z2 is countably compact, Fréchet, and not metrizable. And sigma product, again, to remind you, is just a collection of, it's a subset of the, subspace rather, of the product where at most countably many coordinates are non-zero. And there are also non-Fréchet sequential groups that are countable, and that's due to Protasov and Zelenyuk, and maybe other people as well. I mentioned the free abelian group over a metric compact space. That is always sequential and non-Fréchet. Well, I mean, the compact space, of course, has to be non-trivial. You can't take a single point or 3 points or something like that. And this result is probably done by other people as well. And Protasov Zelenyuk didn't exactly state it like this, but it's a consequence of other results. So can we make this example worse or better, whichever your preferences are? So in other words, can I get in and farther from metrizable, but still stay within the convergence realm? So Shachmatov asked this question in 1987. So this is the 30th year anniversary of this question this year. And he asked, does there exist a countably compact sequential group that is not Fréchet? And he also asked variations of this question about pre-compact and pseudo-compact. And a few years ago, I found a consistent negative answer. So there is a model where there are no countably compact sequential groups that are not Fréchet. Or you can take it as every countably compact sequential group is Fréchet. And so does there exist a consistent example? And of course, the natural way to look for such an example is to have something like CH or diamond, and that's what I'll discuss next. So this summer, Dima and I worked on this problem, and we managed to come up with a counterexample so that there is, using diamond, there is a countably compact sequential non-Fréchet group that is also Boolean. And Boolean groups are kind of a go-to for constructing pathological examples, and the reason is that there's one less thing for you to worry about. If the group is Boolean, then you don't have to worry about inverses. You're essentially dealing with semi-groups only. And in this case, however, as I'll talk about a little later, it's a bit of a liability. However, it's unclear how much of a liability Boolean groups are, because if you start hoping that the extra algebra in non-Boolean groups makes things easier, that's probably not exactly true either. Also, this example is not very structural, so it's a construction that kind of builds the topology from the ground up. There is no natural property that would guarantee that the group is non-Frechet. And one way of making it structural would be to embed Maruvka's, standard Maruvka's compact space into this group. And then, no matter what you do, how many sequences you add, you can't mess this up. As long as you end up with a sequential countably compact group, then you will be guaranteed non-Frechetness in the end. And I tried to have a kind of a simple-minded, very straightforward version of this construction by starting with a Maruvka space, having a natural embedding, and then adding sequences. And that construction not only didn't work, I can prove that it cannot possibly work. So then I had this question: is it possible to actually do this group where there's a good witness for non-Frechetness? The second question I have about the group, I'll talk about the construction a little later, but just to keep this question in mind, whether this group can be made co-indestructible. It cannot be made co-indestructible in the real sense, because once you add a real, you poke a hole in a Cantor set. Once you poke a hole in the Cantor set, you put a copy of the irrational, closed copy of the irrationals inside the group, and that destroys sequentiality right away. So it cannot be truly made co-indestructible. However, the completion process is Borel in nature, so you can describe what the completion of this group is, and Cohen model itself has really nice sequential properties. So if this group will be allowed to live in the Cohen model, there are all sorts of strange pathologies happening in that model. So let me talk about the obstacles. So the construction works in not unexpected way. Michael talked about how they build sequential groups, and it's essentially starting with a group and then adding limit points for sequences. There are two difficulties. One difficulty that's immediate if you try to use pure CH, and I don't know if you can, but if you try to use pure CH without any additional help, then there is no immediate guarantee that the group is not going to be non-countably tight in the end. So you will have these nice sequential properties at the bottom, but the topology might not be sequential. So a lot of, as a matter of fact, pathological examples of sequential groups are constructed with this twist. So the sequentiality is destroyed not because there's some kind of combinatorial breakups of convergence at the low level. The sequentiality is destroyed at large. So they will have groups that are Frechet, but the product is not Frechet. But it's not Frechet because there is an uncountable set that doesn't have a countable, it doesn't have a convergent sequences poking out of it. So that's the first example, and you can overcome that by using diamond and guessing future closed set. The second example was obstacle is a somewhat more combinatorial annoyance, and that is, if you try to do what Michael did in this add sequences, he mentioned the difficulty that in order to keep the group Hausdorff, you have to make sure that those sequences kind of align with the homomorphisms that you started with. You have to do that here too, but there is an extra difficulty, and that is once you add a convergent sequence, you've committed to adding a whole group that's spanned by that convergent sequence. The problem with that is that group is not really very free in the sense of the topology it has. That group must be metrizable. You can prove that since you're dealing with precompiled groups. So once you add a convergent sequence, you add a portion of your group that must be metrizable. It must be homeomorphic to, of course, the rationals. So if you don't add anything else, if you don't complete that, then you destroy sequentiality in this one step. And if you have to do it, and it might not be a problem for some people, but if you do it continue, whatever, omega 1 many times, however long the induction takes, then I don't really know how to collect everything back together, because those points must be in the group. So once you add a convergent sequence, you must have the closure, and that's a counter set. So you can't keep your object countable. You have to keep some kind of countable handle on your group, but you can't really make the group itself countable. So that leads to another complication. What you're adding is are really faceless groups. So those are all the same counter sets. I mean, there's no nice ordinal invariant distinguishing one counter set from another. So there's no scatteredness that you can kind of hang on to. And the only way you can encode all the information, the preservation and everything in your group, is by doing it algebraically. And so your algebraic structure must compensate for the lack of topological structure. So the reason I talk about precompact groups is that every countably compact group is precompact, and precompact just means it embeds into a compact group. By the way, all the groups are Hausdorff and regular, so by embeds I mean in a nice group, so it's not some pathological embed. And the next difficulty that you encounter is that once you take the completion of that precompact group, it's the same group. You can't get anything. So you're essentially looking at a subgroup of the same group of the counter cube, because Plotkin's duality tells you that all the Boolean groups are the same weight, homeomorphic. And so they have the same topology. They're not just homeomorphic, they're isomorphic as topological groups. So your topology has to be linear, consists of subgroups, so there's not a lot of variation. That puts that much more pressure on on how much algebra you need to use. So then, now that we see that one of the main obstacles is precompactness, is there a way to distinguish between precompact and sequentially compact or countably compact groups? And an actual question is it possible to have a model that differentiates between countably compact and precompact sequential groups? And I'll talk about the natural strategy to look for that. But the question still remains, maybe even though the existence of countably compact pathological groups in this sense is independent of ZFC, maybe the precompact, the weaker property, maybe it exists in ZFC. Because that example, that forcing that kills all the countably compact groups is based on putting a sequential fan in the group. And it's a deal breaker in countably compact case because sequential fan is a discrete subspace, but not necessarily in precompact groups. So that's another question that will appear later. So the natural strategy is to look for a model that differentiates between these two concepts is to find something that cannot possibly be countably compact and try to make it precompact. And that is countable groups, a very natural object to look at. How do you build precompact countable groups? And one of the ideas belongs to Ukrainian, and he said that the best way to, well, not the best way, but he suggested that one might look at groups that are so-called single sequence characterized. And that means that it has the weakest possible topology in which a given sequence converges. It cannot be an arbitrary sequence, but there are plenty of sequences that will give you precompact topology. So he asked the question, is it possible that sequential SS characterized groups, or countable groups in this case, are not Frichet or not metrizable and Frichet. So if that were the case, then we have an automatic, pretty much constructive example of a group that has the required property. Again, that's the result I could get, and that is the topology of every such SS characterized group is analytic, in the sense that the topology itself, if you think of it as a collection of characteristic functions, embeds in the Cantor cube, and it's an analytic subset of the Cantor cube. And that gives a negative answer to Duchamp question, because sequential analytic groups have a very well-defined structure. Turns out, the first result was by Topology and Skategi, and they proved that if it's Frichet, then the group must be metrizable. That was the so-called effective answer to Malikin's question. So that answers the second half of Duchamp question. And I proved that every analytic sequential group is either first countable or K omega. And first countable, of course, gives you metrizable, but K omega cannot possibly be precompact. You can prove that by hand, and there might be a result that is due to Protasis, but I don't know the exact reference. But you can prove by hand that K omega group cannot possibly be precompact. So that means that every single sequence characterized sequential group is metrizable. So that was the wrong avenue to look for a pathology here. So now, what about the general case? So I'm now interested in just the first step. So if you have a sequential group, doesn't necessarily have to be Frichet. I have to point out that there are Frichet, very, very nasty Frichet groups that consistently that are not metrizable. Really pathological groups, and again, Michael Krushak and Ramos Garcia have a paper about a general principle that allows you to build precompact topologies that are Frichet. But the sequential topologies are a different matter, and I don't really know how to answer this question in full. However, if your group is a finite exponent, such as a Boolean group, or the group has a linear topology, and then it doesn't matter what kind of algebra it has, then that group cannot be sequential or non-Frichet. They must be sequential. They must be Frichet. They're sequential. And so now it shows that if you're attempting to build a counterexample, then resorting to Boolean groups is not going to work. By the way, all of these results apply to non-abelian groups as well. Even though Petrarchan's duality doesn't work, but Peter Weil theorem has enough tools to do this. So, and this is the corollary that I mentioned. Every Boolean precompact sequential group must be Frichet. So if you're looking for a counterexample, you must look at some other groups. And I'll mention one possible candidate at the end. So now this is the question that I mentioned before. Does every precompact sequential group, can a precompact sequential group contain a closed copy of the sequential fan? And by the way, that question is about all groups, not necessarily countable ones. And if the answer to this question is no, so it cannot, then that automatically answers the question about countable groups, because they will all contain sequential fan. And also, it will supply the last link in that forcing construction, because that's what the forcing does. It builds a S of omega. And a positive answer will be not welcome. Of course, whatever happens, happens. So this is the question that I mentioned. I don't really know if it works even for Z. So is Z a possible candidate for a group that has a precompact sequential topology that's non-Frichet? And the next restatement of this question, it's not quite restatement, but it's a property which is essentially number theoretic that will allow you to give a no answer if the answer to this question is no. And the property has something to do with so-called Kronecker sequences. So if you start with the standard example is if you start with an irrational generator on a circle and start looking at multiples of that generator. Sometimes you will hit the neighborhood around 1, and sometimes you will miss. The asymptotics of how often it does it are very, very non-trivial. This is kind of a collective Kronecker lemma. Well, not lemma, but the possible collective Kronecker lemma. It would be very strange if the answer is positive, because it seems like you can encode in a very natural algebraic way any function from omega to omega. So that's if the answer to this question is no, then the answer to the question about Z is also no. So there are no precompact topologies on Z, and I'm sure that it'll probably allow one to answer the question about at least the abelian groups in full. Non-abelian groups, as I said, Peter-Weil theorem may come to the rescue, but Peter-Weil theorem combinatorially is very non-trivial, and so non-approximation properties of Lie groups will probably be something to deal with. But that's it.
Anyone have any questions? All right, let's thank Alex again. All right, our next talk is by Sanjay Spadaro. He's going to tell us about discrete sets and our Archangelski theorem.
All right, so thank you very much. Thanks to the organizers for the invitation. And thanks to Gary for being such a great advisor. The last time I was here in Auburn was 7 years ago for my PhD defense. And many of the people who were there are here today. There's Gary, Stu, many others. So that time I was talking about discrete sets. So I guess I'll pick it up from there and talk about some recent results with Angelo Bella from Catania about discrete sets. But before doing that, I'd like to remind a very nice result of Gary, which actually was the starting point for my PhD thesis. He proved a nice result of covers of compact spaces by discrete sets. He proved that if you have a compact crowded Hausdorff space, by the way, all spaces are going to be Hausdorff in this talk. Crowded means no isolated points, so he proved that such a space can't be covered by less than continuum many discrete sets. So that's one contribution of Gary to discrete sets. Okay, so what I'm going to talk about today takes inspiration from a result of Kachuk from the 80s. He proved that you can characterize compactness by its presence on closures of discrete sets. So he proved that a space is compact if and only if for every D discrete the closure of D is compact. Okay, so discrete sets, despite being simple, are able to determine global properties of a space, such as compactness. And there are many other properties. Well, if we restrict ourselves just to covering properties, well, let's look at how this theorem is proved. So what do? You take, if you have a decreasing sequence of non-empty closed sets, okay? Then you can construct a discrete set whose closure hits them all. So what do? Suppose you do it by induction, of course. So suppose that you you have a sequence of points which form a discrete set. You look at a closure. If they hit all of your closed sets, then fine, you stop. If they don't, then you look at the first closed set in your decreasing sequence, which is disjoint from that closure, and you pick a point in there. And of course, if you repeat this process, then you're going to pick all of your points inside that closed set. So you end up with a sequence with a property that if you look at a point, the closure of all the points to the left and the closure of all the points to the right are going to be disjoint. And that yields a discrete set which hits all of your closed sets. So this theorem, and that's how you prove this theorem. And you see that this theorem extends to countable compact, because countable compactness can be characterized in the same way. So every countable decreasing sequence of non-empty closed sets has non-empty intersection. You can extend this, of course, to initial kappa compactness and to linear Lindelofness as well. Linear Lindelofness. But you can't do the same thing with Lindelof spaces. Okay? And that's what motivates Archangelski to introduce discretely Lindelof space. So he calls the space discretely Lindelof. If the closure of every discrete set is Lindelof. Well, many things are known about the spaces. For example, they are linearly Lindelof just because linear Lindelofness is reflected by closures of discrete sets. There are some results which tells you that if a discrete Lindelof space has a small cardinal function, then it is Lindelof. But we don't know of an example of a discretely Lindelof space which is not Lindelof, and we don't know a proof that all discretely Lindelof Tikhonov space, even Tikhonov spaces, are Lindelof. Okay, so we have this problem, or canvas, which has been around for a while, which asks whether all Tikhonov discretely Lindelof spaces Lindelof. And you can even ask for a T1 counterexample. I don't know if there is a T1 counterexample. I don't know any model set theory where there is a counterexample or where all discretely Lindelof spaces are Lindelof. So we're pretty much in the dark as to this problem. Just very special results. So I was very happy when Juhas, Kachuk, and Wilson came up with a weakening of discretely Lindelof, which is pretty interesting. So they call a space, so this is Juhas, Kachuk, and Wilson. They call a space almost discretely Lindelof, we're going to abbreviate with ADL, if for every discrete set there is a Lindelof subspace X which covers it. Of course, every discretely Lindelof space is almost discretely Lindelof, but coming up with an almost discretely Lindelof non-Lindelof space is much easier. Just take an S space, a entirely separable non-Lindelof space. All these discrete sets are countable, so they're trivially Lindelof, but it's not Lindelof. So that provides you with a consistent counterexample, with a consistent almost discretely Lindelof space, which is not Lindelof. I don't know all the ZFC counterexamples, so that's a potentially interesting question. Is there in ZFC ADL non-Lindelof space? In this paper, where they introduced almost discrete Lindelof spaces, they looked at their cardinal properties. They made the following easy observation, that if you look at the first count such spaces, then they have cardinality at most 2 to the C. So if you have a space which is almost discretely Lindelof, so this is due to Juhas, Kachuk, and Wilson. If you have a space which is almost discretely Lindelof, first count, then its size is no more than 2 to the C. Why? Essentially because it's spread. It's the size of the discrete sets are not going to exceed the continuum. So if you have a discrete set here, then you know that there is a Lindelof subspace which is going to cover it. But the space is first countable, so this is first countable too. So this is size no more than continuum. But then every discrete set in your space is size no more than continuum. And we have a result of finally Juhas, which tells us that the size of the space is no more than 2 to the spread times even the pseudo curvature. So the size of X is not going to be more than 2 to the C. Okay? So we use Arcangelsky's theorem here, and so this is an interesting variation of Arcangelsky's theorem. So can you prove that all almost discretely Lindelof first countable spaces have actually size no more than C? That's a natural question. Now, can you step down here? Can you get a better bound? And that's what they asked in their paper. Okay, so are all almost discretely Lindelof first countable spaces of size and most continuum? So with Anzo, first we were able to give a consistent answer to this question, and that's what I'm going to talk about today. And then Juhas, Sokol, and Semicloche proved that this is true for all regular spaces. And we improved that to Eurizon spaces. Eurizon means that if you have a pair of points, you can separate them by close neighborhoods. But the main question is still open. So is it true in ZFC that all almost as continuum first normal spaces, Hausdorff spaces, have size at most continuum? Okay, so this is the question. Okay, so we first proved with Angelo that the answer is yes under 2 to the less than C equals C. And then, using a completely different approach, Juhas, Sokol, and Semicloche prove that the answer is yes for regular spaces. And finally, we were able to modify their proof to make it work for Eurizon spaces. So we went from regular, from P3 to P2.5. We improved by half a point. That's the half a point to go to solve the main problem in this course. Okay, so maybe I could give you an idea of the proof of the first partial result, the consistent result. Let's see. Actually, I could erase the board. We actually proved a bit more than that. So we proved that if you have a sequential, okay, Sasha already gave the definition. So it's a space where if you have a non-closed set, there is a sequence convergent also. Okay. So suppose I have a space which is sequential. Almost as good to the pseudo character is a most continuum. So this means every point is the intersection of continuum many open sets. Then, and you have 2 to the less than C equals 2. Okay, then the size is homogeneous. Okay, so how do you prove this? Well, you see, you have a sequential space, so it's enough to prove that the density is more than C. Because in a sequential space, you get the closure of a set just by iterating omega-1 many times, the closure will be sequential closure over it. So, and every iteration is going to have size no more than C if you start from a dense set of size no more than C. So eventually the whole space is going to have size no more than C. So it suffices to prove that the density is homogeneous. Okay, now suppose this is not true. Then, inside of your space, you can find a left separated set of size larger than this. This is your space. There's going to be a subset of size, so order type continuum plus, see? Okay, such that every final segment is open. Okay, so you construct by induction, you have continuum many points, their closure is not going to be the whole space because you assume that the density is larger than continuum. And so you take a point outside of that closure, you keep doing that, eventually you get a space where all final segments are open. Okay, so L is left separated as size continuum plus. Okay? And now you take an elementary submodel of a large enough fraction of the universe. and you throw in X, L, and a bunch of other things. We are not going to need more than continuum many things. And this elementary submodel is less than C closed. And of course the size continuum. Okay. Now, if you look at the intersection of L with this elementary submodel, well, L certainly is not, L is an element of N, but it's certainly not going to be contained in N because it's just too big. Okay? So we can pick a point outside of N, which is in L. Okay? Alright, so here we have X, here we have L, and here we have M. So we know that there's a point here which doesn't belong to L intercept. Okay, and now using the small pseudo-curvature thing, we can cover X-intercept M by open sets in M which don't contain P. So for every X in X-intercept M, we can find an open neighborhood of X which contains X but doesn't contain P. Okay, using the small pseudo-curvature. So you fix a local pseudo-base at the point X, which belongs to M. This local pseudo-base is going to be in M. It has size continuum. So assuming that the continuum is an element and is contained in M, then that local pseudo-base is actually going to be contained in M, and then you can pick an open set from there which doesn't contain P. Okay, so if you put together all this open sets, then you get an open cover for X intercept M. Okay, now I claim that there's a less than C size subcollection of this open cover, which maybe doesn't cover X-intercept M, but it covers L-intercept M. And that's enough. Why is it enough? Well, by elementarity. Okay, so let me write down the claim again. So the claim is that there is a subcollection of size less than C, right, which covers L-intercept M. Okay, but remember that L belongs to M, and M is less than C closed, so V is actually an element of M. So what this is telling you that M sees that L is covered by the union of V. And then, by elementarity, your fraction of the universe is going to think that too. But now, P belongs to L, but not to the union of V. So if we can prove this claim, then we're there. Okay. All right. Well, if L-intercept M would have size less than C, then this would certainly be true. So let's assume that it's got size C. Where did I put the eraser? Where is it?
On the board, I think. Oh, never mind.
I lost it. Yeah, maybe it fell down.
What?
Can you erase it?
Yeah, it is.
Oh, here.
It's on the desk.
That's not it. That's over there.
Where is it? Yeah, kind of sheet of paper.
Sure.
Oh, there it is. Oh, sorry. Okay. Yeah, so here is L, and here is M. Okay, so if you look at the intersection of L intercept M, of course, if it's got size less than C, then we're done. So like covered by a subcollection of U of size less than C. So let's assume that it has size C. And let's assume that it can't be covered by a subcollection of size less than C of U. Okay? Then we can get inside L intercept M, we can get the right separated subset. Okay, just by enumerating U and then picking a point of L intercept M which doesn't belong to the first alpha elements of U. Okay, so eventually we get a set where every initial segment is open. Okay, and that's size continuum. Okay, so there is R in L intercept M, which is right separated, and a size continuum. Okay, but if you have a set which is both right separated and left separated, that's left separated is a subset of L, then essentially by the L-Dushkin-Miller partition relation, you can find a subset of the same size where the left separating order and the right separating order agree, and that's a discrete set. So there is a discrete subset of R of size continuum. Okay, but now, look, we're almost discrete in Lindelof. We haven't used that assumption yet. So there is a Lindelof subspace of X, which covers Z. But actually, D is covered also by Y intercept M. And that's closed because we're sequential, and M is currently closed. So this also is Lindelof. Okay, that's also Lindelof. But then there's a countable subcollection of U which covers it. Okay, but that's an absurd because when I constructed this right separated set, at some point I had to take a point off that countable subcollection. Eventually I took all my points off that countable subcollection. So I get a contradiction, and this finishes the proof. Okay, so I guess the most interesting questions are, is Hausdorff enough here in ZFC? And of course, can you find in ZFC an example of a normal discrete Lindelof, non-Lindelof space? And I guess I'll stop here. Thank you very much.
He's going to tell us about his very favorite thing.
Sit down, Michael. All right, thank you very much. I'd like to, of course, thank the organizers, especially Zichen Feng, who I think did a lot of work to bring this together. I want to wish Gary happy birthday, and thanks for inviting me. I'd be very happy to celebrate your birthday and everything you've done for Topology and the community. So, and I was thinking for a while what I wanted to talk about, and I went back. I've had a very nice opportunity to collaborate a few times with Gary. And the last paper I wrote with Gary, I went back to look at recently, and then also went back and started looking at Gary's contributions over the years. And I noticed that this joint paper actually touched on 3 things that Gary has thought a lot about, I think, since early in his career, which are in the title. And so as I was looking back, I went back to 1976. And then I started, of course, getting nostalgic not only about mathematics, but about 1976, because that was the year that Nadia Comaneci was in the Montreal Olympics. My beloved Kansas City Royals won the American League West, led by George Brett. Of course, I live in Toronto now. I was surprised to realize that's where they built the CN Tower. And maybe for this area of the country, you all remember Jimmy Carter was elected. And this guy introduced the following topological game. So it was really a big year. Now that wasn't 1976. I think that was 1986 at the TopoSim. At least I found it on the TopoSim website. So I emailed Peg and asked her if she had an older picture of Gary, or something closer to 1976, and she sent me that picture. So I hope that doesn't, I think it's a great picture. There are 2 cats there. I don't know if you kept those cats or not, but I'd like to think that you named those cats Point and Set. Enjoyed watching them play together. Because in 1976, you introduced a game in this paper, Infinite Games and Generalizations of First Countable Spaces, that involved 2 players, Point and Set. And it's played with respect to a point in the space. And Set picks a neighborhood of the point X, Point picks some other point in that neighborhood, and you continue in that way. And of course, Set is trying to force the point player to pick a convergent sequence to X, which of course they can do if the space is first countable. And anyway, so this was introduced in this paper. I think some basic things were proven about it, some interesting questions were stated. And it was later that it was, I think, uncovered that, I think it's due to Sharma, is that correct? Okay. That point has a no-win strategy is exactly characterized by being Frichet and alpha 2, which of course was a class of spaces I think was introduced later by Arhangelski. But so he had great intuition about games and topological games and found this very nice game that characterized this very nice property. And of course, the alpha 2, these class of spaces played a very important role in the study of Frichet topological groups and other related things, and including other papers I wrote with Gary. And another version of this game, Gary wrote 2 other papers using different versions of this game, where instead of fixing a point to start with, one fixes a set, but plays the same type of game. Set picks an open set around an open neighborhood of that set. Point picks a point in the open set and continues in that fashion. And, oh, I forgot. I think the original notation was O, but I grew attached to the 2 cats at the beginning, so I changed it to set and point. But O wins the game if the sequence of points converge not to X, but I apologize, to the set, H. Okay, so that means every neighborhood of H contains a tail of the sequence. And he used this game to characterize coarse and compact. So X is coarse and compact if only if set has a winning strategy in the game on the square of the space with respect to the diagonal. And in the other paper, used it to characterize Eberlein compact as exactly those compact spaces so that set has a Markov winning strategy in the same game on the same space with respect to the diagonal.
Remember what spaces, so X has to be compact?
Yeah, this is for X compact, yes. Of course, yeah. Right, of course. You can play the game on any space, but the theorem requires X to be compact. Okay, so he, I don't want to spend too much time going through other contributions, but another one that was close to something I thought about recently is the class of proximal spaces that were introduced by Jocelyn Bell, who used them to study the uniform power, the uniform box power of a topological space, and to analyze when they're normal. And Gary, with his student Stephen, proved that compact proximal spaces are coarsen. And then that was a key result in Rodrigo and I proving, or answering a question of Nikos, that the uniform box power of a compact proximal space is proximal, so that this property is preserved in uniform powers. So that's maybe a bit technical and specialized, but Gary's thought about topological games for a long time. Another thing he's worked a lot on, of course, is spaces with countable network weight. So that's the cosmic spaces of the title. So a space is cosmic if it has countable network weight. And I think this paper in the Transactions from '89 had this beautiful result under PFA that for the class of cometrizable spaces, so a space is cometrizable if its topology is obtained by refining a metric topology so that every point has a neighborhood base of sets that are closed in the original metric topology. So many natural constructions of counterexamples, you begin, for example, with the topology in the reals, and you refine the topology, and you end up with a cometrizable space. So the class of cometrizable spaces, we have all of these things are equivalent. The omega power is hereditarily Lindelof, omega power is hereditarily separable, x squared has no uncountable discrete subsets, and that's all equivalent to x having countable network weight. And this is a nice result because all of these equivalences are still open in general, I mean consistently and presumably under PFA. I'm not sure of all of them, but I know Heimliski asked if the combination of x omega, hereditarily Lindelof, and hereditarily separable implies countable network weight. Spread being omega, that's an open question. And the analysis of that plays a very important role in the basis problems that were talked about earlier. So it's, I think, really a fundamental, important result in that area. And I'll get to it in a moment, but whether or not some nice property stronger than the space being hereditarily Lindelof, whether that implies countable spread consistently, is a common theme, and they're usually very interesting problems of those types. And I want to mention one by the end of the talk that you may not have heard of because there's only our paper about it and no one has really, I think, thought any more about it since then. He also, so this is another contribution related to countable network weight. He proved this nice thing about Lindelof sigma spaces with small diagonal have countable network weight under CH. And of course, this is all other results related to Houchet's problem about metrizability of compact spaces with small diagonal. Okay, and of course, D spaces, which are very popular in America. I hear now they're not popular in Japan, but not only America, Canada as well. So North America. So I think we all know what it is, but it's okay. D space, if you look at a neighborhood assignment to a topological space, you can find a closed discrete set, whose neighborhoods cover the space. And of course, most of the research and most of the interest in this class is driven by Van Douwen's question of whether or not Lindelof regular spaces are d-spaces. So Gary has contributed in this area as well. He wrote, I think, a very nice survey and a nice paper, Notes on D-spaces. There was work by Fleischer and Stanley on n-sticky neighborhood assignments, and he extended that work a little bit and proved some nice results, including that coarse and compact spaces are hereditarily D. But what I want to talk about is the paper we wrote together that kind of brought all these three areas kind of where they intersected. So there was a paper, I think it was called A Game and Its Relation to Network Weight in D-Spaces. And it was based on a game that essentially was trying to distill a proof that one might try to write down that a hereditary Lindelof space or that a Lindelof space is a D-space. In more generally, natural way to try to prove that space is a D-space. So you begin with, of course, a topological space in a neighborhood assignment. And what you might try to do is pick a closed discrete set and look at the neighborhoods associated to that closed discrete set, see what's covered, okay? And then choose another closed discrete set outside of that. So anyone who's ever tried to prove that a space is a D-space has tried this. And you look at the neighborhoods which cover those, and you continue. And if you can cover the whole space after omega steps, then the union of those closed discrete sets you chose is closed discrete. Okay, and then you have that it's a D-space. Okay, now if you know that your space is Lindelof or hereditary Lindelof, you know that you should be able to choose a countable collection. So you might try to just choose one point at a time instead of a large collection. Okay, so we play a game. Again, Gary's cats are playing set and point. And set begins by just choosing a subset. So you should think of D0 as a subspace, or if you want, D0 as some collection of points related to a neighborhood assignment. But only in the first inning does set play a collection of points and the neighborhoods just to those points. And then point picks one of those points from D0. And then in each subsequent inning, the neighborhood assignment is fixed, so that neighborhood assignment chosen at the beginning plays through the whole game. So set plays a subset, and point plays a point in the next set chosen. And point wins. Okay, so point is trying to make sure that the chosen points witness the space as a D-space. So if the union of neighborhoods chosen cover all the rest of the points. Okay. So if you think of this in the same way, if you think of a play of the game where set plays a neighborhood assignment and plays the whole space, point chooses a point, then set plays all the points not yet covered and continues, you would see that a winning play in that game by point would witness that the space is a D-space. Okay. So if set has no winning strategy, okay, so if, you can prove that if set has no winning strategy, then the space is actually hereditarily D. And of course, to prove that the subspace is D, you look at the opening play by set. And moreover, you can prove the space is hereditarily Lindelof. Okay, so it's not hard. It's not hard to do. On the other hand, if the network weight of the space of X is countable, then you can actually write down a winning strategy for the point player. And the main question that we have left from this paper is the converse to this proposition, which looks maybe a little innocuous, but maybe I want to try to convince you that it might be a little bit interesting. Okay, so of course, point having a winning strategy is stronger than set having no winning strategy. So a counterexample to this question would have to be a very nice hereditarily Lindelof space with uncountable network weight. Okay. So it's again, it fits into that same class of questions about a take a strengthening of hereditary Lindelof and ask, can you prove that everything in that class has countable network weight or not? Okay, so let me remind you of another question in that same vein due to Tkachenko, which is about weakly separated subsets. So a subset of a topological space, this is maybe a generalization of right and left separated. So a subset is weakly separated if there's a neighborhood assignment. So when you look at any 2 points, either one point is not in the other's neighborhood assignment or vice versa. So for example, if you're left separated means your neighbors look to the right. So yeah, so the point on the left is not in the neighborhood of the point on the right. And vice versa if it's right separated. And it was, Tkachenko asked, is it consistent? Presumably under PFA is what the conjecture is, that if a space has no uncountably weakly separated subset, then it has countable network weight. Okay. So, there are some, of course, consistent counterexamples. And let me mention just one of them, because it's typical of, I think, all the examples. So you have the plane, nicely constructed subset of the plane, and one takes essentially bow ties as a neighborhood assignment. So I was very upset, Santi, when you erased Nicholas's picture from earlier today of the butterfly point. I was just going to use the same picture.
You have 5 extra minutes.
So one thing to notice about this, the fact of the construction is there's nothing special about taking the bow ties oriented in this way. The space is very symmetric. You could have rotated the bow ties by 90 degrees and obtained an example with the same properties. Okay, because this is the way the space is defined. And the other examples are similar. So it's like the Sorgenfrey topology. The neighborhoods look to the right or the left. Doesn't make any difference. It's the same nice space. So let me just put the example there again as a reminder. And the statement, that I pointed out, the dual topology given by rotating by 90 degrees has the same properties. So then the strange property that we focused on was this definition. A subset of a space is dually weakly separated with respect to another topology if you have neighborhoods at all the points with respect to the given topology and neighborhoods with respect to the dual topology, so that for any 2 points you have the same relationship but you're looking at the 2 topologies. So either X is not in Y's neighborhood with respect to the new topology or Y is not in X's neighborhood with respect to the original topology. So all of these examples that are hereditarily Lindelof, that have uncountable network weight and no uncountable weakly separated subsets, all are kind of built in a symmetric way so that there is a natural dual topology that dually weakly separates the entire space using the dual neighborhoods and the original neighborhoods. In the same way that the Sorgenfrey line is. And what we proved is that if point has a winning strategy in X, then X has no uncountable subset which is dually weakly separated with respect to any other hereditary Lindelof topology, which essentially kills off all of those other examples, consistent examples of spaces with uncountable network weight that have no uncountable weakly separated subsets. Okay, so that's the question. So if point has a winning strategy in the D space game, I guess you could call it, does X have countable network weight? And I guess this question is interesting because it really requires construction of a new type of example witnessing, for example, a counterexample to Tkachenko's question. So that's pretty much all I wanted to say. I could have possibly gone into more details with proofs. This is a paper that we wrote together. Again, I would say that I find this a nice paper in terms of understanding Gary's contributions because of its intersection in these 3 areas. And as far as I know, it's Gary's only foray into the theory of bi-topological spaces. So let's hope it stays that way. Anyway, thank you very much.
Any questions?
I got a question.
Yes.
So what about, do you know anything about if a point has a Markov winning strategy?
A what?
A Markov winning strategy in the D-space game?
Yeah, I think at the time we thought about some of those things, or I did at least, and I didn't get any insights into it. There are obviously lots of things that could be looked at here. One could look at the game where one doesn't choose a point, but one chooses a closed discrete set and proceeds, and see if there's something interesting you can say about that game and the class of spaces for which a space one of the players does or doesn't have a winning strategy. Yes?
Yes, Sharma did this thing about if point does not have a winning strategy. Gary also talked about what he called capital W.
Are you talking about the original, the game from '76?
Yes,
Right,
the
yes.
one that Sharma did that
Yeah.
thing of.
Right.
And right now, I think we have only one example of a space where
The game is undecided, or?
no, that's another, no, where every countable subspace is first countable, but the first player, the set player still doesn't have a winning strategy.
Ah, okay.
Yeah, and that's very nice. It's an Ehrenstein tree, and with all the usual topology, and there's a nice countable elementary submodel way of showing that the set person still doesn't have a winning strategy there.
It's not a person, it's a cat. Okay. Yes, Gary?
About the cats.
Oh, yes, please. I wanted the story of the
We
cats.
didn't name them set and point. We named them Beta N and Beta R.
Oh, so there are much more complicated cats than
But at least one of them was a set.
Anyone else? Let's thank Paul again.
What is the
Cord down.
We'll go ahead and get started. Our last talk before coffee today is by K.P. Hart, who's going to tell us a story.
Thank you. I hope you don't hold it against the organizers for inviting me. Okay, Gary and me, it sounds maybe a bit self-centered, but I do have a few things in common with Gary. And one of the very first things happened, imagine if you will, me, but 40 years younger. Hard, I know. My advisor, Martin Rees, taught a course on generalized metric spaces. That's not Martin, but it's a nice picture from campus here about somebody teaching. You can see it's not Martin because I think he never taught with a tie. If you look very closely, this one is actually wearing a tie. But generalized metric spaces and the M1, 2, 3 classes also appeared. And Martin mentioned during the class, although he didn't give the proof, that someone named, and we weren't quite sure how to pronounce this at the time, Grune had proved that M3 implies M2. Of course, in German you would say Grünhage, but that's not what you would do here, yes. This got me, I was young and interested in this kind of thing, and Martin actually had a copy of the paper, and I read it, and so I owe my first seminar talk to Gary. Because Martin said, well, why don't you talk about this in the seminar? And one member of the audience is still in this audience as well, and he's actually standing up there in the back. So you can ask him how bad the talk was. I have one question though. It struck me, I was reading the paper a few days ago, and that was about this notation here. If you look, I don't know if you see it, it's a V on the line, it's an F sort of as a subscript, and the N here is back on the line again. This is typewriting, and in these days of tech, I have no idea how you would, what was meant. Was it to be V sub F and the N simply on the line? Was it to be V sub F to the N? Or were you meaning something like this, sort of the nth iteration of doing the VN? I think if I were to take it now, I would take the last one. Right. Okay, that was part one. That was very short. Here's a longer part. I discovered, I didn't know this, but okay, I occasionally send in solutions to monthly problems. And usually I don't really go back and say, well, what happened to my solution? But in 2000, suddenly, out of the blue, an email from Gary, congratulations on getting a solution published. And I, what? Well, it turns out that monthly issues were arriving earlier in the US than in Europe, I guess. It turned out that one of my solutions was published, and it also turned out that Gary is also an avid reader of the monthly problems, solving them. And, well, he's got one up on me. I don't know if you recognize this building. This is called GCHQ. It's what goes for, it's the UK's version of the NSA, of the National Security Agency. And they have a file on Gary. And here's why. This is in the monthly of 2000. There is a problem proposed by, I don't know, that's somebody you apparently know from Georgia, Curtis Herring. I don't know the person. And Gary. Huh? Okay. Anyway, I'll read it to you in case you can't read it. You take two infinite cardinals, kappa bigger than lambda. You have a space with at least kappa open sets. And if every open cover of X that has exactly kappa open sets is a finite subcover, then the same holds for covers with exactly lambda open sets. If you get bored, you can try and solve it yourself. Now, 1 year later, I was looking through the monthly issues in preparation of this talk. You can get this, and here you see where the file from GCHQ comes from. The GCHQ apparently has a problem-solving group, and they solved Gary's problem. At least more people did, but their solution was published. So Gary, they know you there. I also sent in a problem to the monthly, but they didn't get mine. Didn't take mine, so score 1 for Gary, 0 for me. Almost a year ago, I had sent in the solution to this problem as well. But Gary's solution of Gary's appeared. Here's another problem you might want to think about if you've got nothing better to do. You take a set, binary operation, and you would like to have an uncountable set with a binary operation so that all the closed under the binary operation sets form a chain. So say a group and all the subgroups form a chain or something like that. Well, you can see the first few lines of Gary's solution. There is more, but I'm not giving it away. I'm only giving away what Gary did. A commutative operation on omega 1. Then he showed it cannot be associative. Think about that. And then he also showed that it cannot be done on omega 2. You cannot get further than omega 1. And then, of course, people, can you do it on the reals? Yeah, well, if and only if CH, apparently. I was an also-ran. I submitted the solution, but I didn't make it because I only had a subset of Gary's results. And there's a new race on. This guy, Greg Ullman, I don't know who he is, but...
He's a good friend. He was at Ohio University.
All right, well, the previous problem was posed by him, and this one is posed by him as well. The name struck me. This is really, it's a lot of reading, but the problem asks, okay, you have a family of functions from a set to itself. That's the F. And you can call a subset of the set X closed under F if every member of that particular set Y is mapped to Y under every map in F. Fine. Axiom of choice given, although I think you don't need it. There is an uncountable collection of functions from just the natural numbers to itself with the following property. If you take a proper subset, of course the integers are closed under the mappings, but if you take a proper subset that is closed under the family, that has to be finite. That's demand 1. The other one, if you leave out one function from the family, then suddenly you get an infinite proper invariant subset. Can you do this? Gary has a solution, I have a solution. You figure one out for yourself. I think I won't win because I reread my solution and it's a bit too short, too terse for the monthly, I guess. It should need a little bit more explanation. But anyway, may the best solution win. And okay, now I get to sort of the bigger part. The third time Gary and I, well, not collided, Gary influenced some work that I did together with Alan, because the rest, Alan shares the blame for what is coming now. Small diagonals, Paul already mentioned them. Here is the definition of small diagonal. A small, yeah. You know, the definition is due to Houshek, except he defined the negation of this. And people thought that the negation of Houshek's definition was more useful. An omega 1 accessible diagonal is one such that you can create a converging sequence of length omega 1 to the diagonal, in the sense that every neighborhood of the diagonal contains a tail of it. And if you negate that, then you get the definition of small diagonal. Fine. And of course, we don't want the set already to live on the diagonal if it converges. Never mind. G delta diagonal is small. So metrizable spaces have small diagonals. Just in case you didn't hear me, I'm having it on the slide as well. If you look at compact small diagonal spaces, Paul mentioned the problem, I think. The question is, does every compact Hausdorff space with a small diagonal, must it be metrizable? I talked about this 2 years ago in Galway, and the title of my talk was A Class of Invisible Spaces. Because we don't have any, let's say, instructive examples of compact spaces with small diagonals, because we simply don't know any non-metrizable one, consistent or otherwise. For all we know, everything is metrizable anyway, as I'm talking about nothing, basically. So how do you, in these modern day and age, how do you tackle a space with a small diagonal? Well, there's something about the omega 1 sequences. So you use elementarity. Elementarity substructures of what? Well, some H kappa over the whole universe, depending on your Platonic or otherwise point of view. You stick your space into the first one, the first elementary substructure, and you build it up because you want to do something omega 1-ish. Okay. And then we call that an elementary sequence for a space. And if we simply take subspaces of Tikhonov cubes, then we can talk about restrictions of points to ordinals, because every point is a function from an ordinal to a unit interval. And from such an elementary sequence, we could probably extract, or maybe, a sequence of points such that, for example, this happens. X alpha and Y alpha are the same as far as M alpha is concerned, but they're not. And together they belong to the next one. One of the X alpha, for example, may be constant. There's nothing against that. It just means that apparently you're trying to converge to the one constant X somehow. Now, Gary characterized small diagonal, complex small diagonal. If you take an omega 1 sequence of pairs, then it's omega 1 separated, meaning that you can take an uncountable subset of the index set, and then the first coordinates and the second coordinates have disjoint closures. And that is what keeps the points away from the diagonal, so to speak. In fact, I mean, this is not a very deep generalization or anything, but it suffices to look at elementary sequences of points. So a compact space has a small diagonal if every elementary sequence is omega 1 separated. Now, a compact space is metrizable if the diagonal is a G delta set, and a compact space is metrizable if every elementary sequence of points does not exist. Because if you try to build this, if you try to build a sequence like that in a compact metrizable space, it will just fail after a while because of the countable base. So now you have the difference between compact small diagonal and compact metrizable. Every elementary sequence is such and such. There is no elementary sequence. So what do we want to show? If we want to show that all small diagonal spaces are metrizable, we want to show there are no elementary sequences, for example. Okay, it was already asked, but now we ask it once more. How does that work? Well, there are tons of positive consistency results about this question, and that's what makes it frustrating, you know. Give me an example of a complex space with a small diagonal. Oh, here's a metrizable one. What else? But Gary showed that in the paper that Paul referred to, that if you are hereditarily Lindelof, then you are metrizable. And how does that work? Well, let's look at our elementary approach. Take any uncountable set, look at the first coordinates, that set is Lindelof, because we are hereditarily Lindelof. And that means that actually inside this index set, there is what Engelking, I think, calls a condensation point of the set of first coordinates. Every neighborhood contains uncountably many points of the whole sequence. Now, hereditarily Lindelof, hence first countable because we are compact. So that M delta plus 1 knows this and says, oh, I have a countable local base for the point X delta. Well, then we're done. Because after that, we cannot distinguish X alpha and Y alpha anymore on the basis of the local base for X. So the sequence, we don't get this separation business anymore. Okay, now that is a very nice proof and it works very well. And what Ellen and I did is make it more ugly and get maybe, well, the last drop out of it that we can. So what do we need in this proof? Okay, we used first countability to say, well, you know, the tail of the sequence is no longer separated. And we needed a point where the first coordinates were going to accumulate, have this condensation property. Now, it wasn't really necessary that it was a point in the sequence. Because if we take any point in X intersect the model, the big substructure, it gets captured in some M alpha. Then the M alpha plus 1 have the countable local base, and because it's a condensation point of the whole sequence, you get what you want. And to get the point, we only need to know that X intersect M is Lindelof. We don't need to know that the sequence itself forms a Lindelof set. And, okay, we need a local base at that particular point to make everything work. And here's the thing. We need just one elementary sequence of substructures, omega 1 long. Take the union of the things, intersect with X, and if that particular subspace is Lindelof, then we can actually prove that the whole space is metrizable, because then we can prove that it's first countable. Why is that? Well, if it isn't, then that's witnessed by a point. The first elementary substructure in the sequence already knows that there must be a point where the thing is not first countable by elementarity. And then we can construct an elementary sequence that has the X constant, and the other coordinate is going to converge to it. So what's going to happen, it's going to converge to it, and I'm going to show you how. We take any old uncountable subset, because we have to show this for every uncountable subset, but we could take the whole sequence. We take an accumulation point, complete, in M, because X intersect M was Lindelof, right? And now what happens is that these two are going to be the same all the time, because of the, because of what? Okay, y is a complete accumulation point, so you look at the neighborhoods of y, and they're going to have to coincide with the x alphas all the time. And there you go. We have a point in M that is apparently equal to x on the coordinates in M. Well, that means that the 2 points have to be equal. And then we get that the sequence converges to x, and then we contradict the separation. Oops. That finishes the proof that sort of the minimum thing you need to make Gary's proof work was that one thing. And that's it. We still don't know if every complex small diagonal space is metrizable. Maybe Gary can do something about that now too. Please. Okay, somebody was asking about what?
That's what Gary said to me.
Well, I'm throwing it back at him. So this might be some way to attack the problem. You know, find in a very fancy way some elementary sequence that actually does the trick. I have no idea how, but who knows? People were asking me about this shirt. Well, as you all know, Gary is a nice person, and when Springtop was here in the 90s, he lent me his car, and I gave it back in one piece. But I went to Tuskegee, and I was really impressed by what Tuskegee University looked like. I can recommend you to go to the George Washington Carver Museum there. Anyway, and this is what I wanted to say at the end. Thanks for all the fun, Gary.
Yeah, what language and what's the translation of it?
Irish.
So I thought, okay.
I have a story to tell. And I checked with Aisling, it's completely correct.
How do you pronounce it?
That I don't know. I didn't try. I'll ask her next time I see her, and then I'll tell you. Right? I have the feeling that the pronunciation rules are quite straightforward there, so you might just use the syllables that you have, and maybe the A would be A, and after that everything will fall into place. So let's have a look. My guess is Tashelina Ramadan. But I'm willing to trade it for another guess.
Didn't you also show that under CH, for example, every compact space with small diagonals and metrizable?
Yeah, that was covered by there are tons of positive consistency results.
Actually, that was Tushak's original question.
Under CH. Yeah, okay. But anything else still open.
Why did he care only about CH? Why did he care only about CH?
Because I think he proved something under CH and he was asking if this is correct. I think.
Well, if the weight is Aleph 1, then you have a uniformity of weight Aleph 1, so you know that it's not going to happen.
I should point out that Gary had this paper in which he showed that if you weaken compact to countably compact, you get a independence result.
Or just the consistency of it?
No, it's independence. Both ways.
Okay.
What Russian mathematician who spent some time here in the United States showed that under diamond plus, there is a countably compact space with a small diagonal that's not metrizable.
That rings a bell. That was Pavlov.
Pavlov, yeah. So that was another direction. What was it that you did that Martin's axiom, something implies that everything
I needed more than Martin's axiom, but I forget what, it's something that you were involved
Right,
in.
right. Yeah, actually, it was consistent with CH, so it's consistent with CH both ways.
Yeah,
Yeah,
right.
and that was it. Todd and I had shown that in a first countable, countably compact space, PFA shows that every, well, that was known, that was really that PFA does this, but then Todd and I showed that it's consistent with CH also, that every first countably compact space is either compact or contains a copyable megaphone.
All right. So anyway, that takes care of the countable compactness, but still the compactness remains. Anybody an answer?
Any further questions? All right, well, coffee in 5 minutes, and then we'll meet back here in 35. First, let's thank KP one more time. Our final talk of the day will be delivered by Justin Moore, who's going to tell us something about sigma scattered linear orbit.
Okay, so I guess I'll begin with an announcement that I would appreciate getting if I was flying tomorrow. And that is, don't forget that Atlanta is an hour ahead. Unfortunately, I'm going to have to go to the airport, or go to Atlanta tonight. I won't, because I'm flying early in the morning, but just keep that in mind if you're driving to the airport tomorrow. I was trying to think of when it was that I first met Gary, and it's, in my case, it's maybe a little bit nebulous in my mind because perhaps I first met you, and we first crossed paths at least maybe in Delaware in the spring meeting in '95. The question is whether you were there. I was an undergraduate at the time. I wasn't producing any theorems, so there's no reason why you would have noticed me. Yeah.
I guess you didn't go to my talk.
The amount that I got out of the talks that year was minimal, but so I apologize for that. Okay, so I want to talk about non-sigma scattered. Now, I made an apology to Gary that this isn't really topology, and Gary said no, but it is. And actually, I had considered talking about some of the things that fortunately Peter said something about, which was the spaces problem for the first countable spaces, uncountable first countable spaces. I didn't really have much to add to that. I visited Auburn, 2009 or 10 or something like that. And we talked some about that, spun our wheels on it, and I haven't made any progress since. We didn't make any progress at the time. And at the end, I felt like I would rather say something about something that I could say something about instead. Okay, so let me begin by kind of telling sort of the very short version of the story, and then a little bit longer version of the story, and then we will get some into the insightful analysis. I don't know that we'll get to the intricate combinatorics, but that's maybe for just reading. Okay, so there was a conjecture of Frazé, I think 1948, that the countable linear orders are, well, quasi-ordered. So if I less than omega is a sequence of countable orders, then there exists a balance of J such that Li embeds into Lj. So sometime later, Leber proved that this is true. That he proved that something called the sigma scattered linear orders I need to say what the sigma scattered linear orders are. So L, since it's later, 73, 71. L is scattered if the rationals do not result at L. So for instance, every well order is scattered, but also every ponderous well order is scattered and disclosed under taking sums and so on. So you can have things like integers are an example of a scattered linear order, two sequences converging to 0, but also much more complicated linear orders. And L is sigma scattered. It is a countable union of scattered suborders. Now,
Justin,
yeah.
it's clear in my head. If you take the rationals and replace every point by the integers, that doesn't count?
You take the rationals and replace every point with the integers, that does not count, because you take the 0, each of the zeros, that is a copy of the rationals.
Yeah, so it's got nothing to do with isolated points and everything.
No.
No topology, it's just orders.
It's just order, yeah, that's a good point, is that, and this is maybe why I don't entirely agree with Gary when he said they talk about linear orders, it's just about topology, but there are some differences along these lines. Now, let me just sort of mention an example, which is a good one to keep in mind. It's tempting, of course, every countable linear order is sigma scattered. Every well order and converse well order is sigma scattered. They're closed undertaking, say, lexicographic, well, closed undertaking sums. So if you have a linear order L, which is sigma scattered, and you replace each of the points with a sigma scattered linear order, then that sum is, the sort of lexicographic sum is sigma scattered. And it's maybe tempting when you first start thinking about these to think that the intervals, like every point should have a neighborhood which is somehow small. But that's not necessarily true. Sort of a typical example is if kappa is any, say, infinite cardinal. I suppose this makes sense for finite cardinals too, but if you take the collection of all x in q to the kappa such that the support of x is finite, and you give this Lax ordering, then this is sigma scattered. And for emphasis and kappa lengths. So, meaning that every interval has size kappa. So there's no notion of, well, we're just going to throw away the small intervals and then that will create some small intervals and we keep throwing them away until we get rid of the whole order. So this is, in some sense, this looks rather large, but it's actually small from this point of view. Now, around that time, okay, so let me sort of flash forward to the present. Matt Foreman, I was at a conference recently where Matt Foreman was giving a talk and he said, never bury your lead, and this is in that spirit. So you state the main result, and then we'll go and kind of give some context for this. So this is my student, Hossein Amirandi, myself. This is sort of to appear, and it's, if it is consistent, or sorry, if there's a supercompact cardinal, then there is a forcing extension with the following. Okay, one is that CH is true, and two is that there are no minimal non-sigma scatter. So what do I mean by minimal? I mean, we're thinking about the class of all linear orders as being quasi-ordered by the embeddability relation. Right? So there's an actual equivalence class there that each, A is equivalent to B if A embeds into B and B embeds into A. And you might ask, is it possible to extend Labor's result to a larger class, which is, say, hereditary, and which is well quasi-ordered by the embeddability relation? Well, if that were true, then if you looked at the class of all non-sigma scattered linear orders, there would have to be a minimal element because it's well-founded. And this says that you really cannot extend Labor's result to any broader class than this model. Right? This is as good as you can do. And I'll also mention that it's the same. That PFA plus implies every non-sigma scattered linear order contains X, C minus C, or a Baumgartner type. Or its reverse, where C is any Countryman line, I should say what that means, and X subset of R is cardinality alpha. Okay, so I need to say what Baumgartner type is, and I need to say what Countryman line is. We'll get to that. Okay, but this is kind of the end of the story, the punchline in a way. And both of these results are in a paper which is to appear in the Math Research Letters. Okay, so the next part of the talk, I'm going to explain to you why, what led to this. Why would you want to prove this? Okay, so back to the 1970s and 1980s. Okay, so at the time of, sort of right around the time of Labor's result, there's a theorem due to Baumgartner. This is 1973, where he proved that it is consistent with ZFC. And here, even though this 4PFA wasn't formulated at the time, but it's immediate from this and follows from PFA that every two alpha-1 dense subsets of R So aleph 1 dense just means that every interval has cardinality aleph 1. Now it's easy to show that if you take any subset of R of size aleph 1, you can throw away the countable intervals and get something which is, okay, it depends on how you define aleph 1 dense, whether you mean that just in the order theoretic sense that every non-empty interval has cardinality aleph 1, like every interval has cardinality aleph 1, or you mean externally that if you have two reals that they have aleph 1 mean points in between them. So if you just take it in the abstract sense of linear orders, every uncountable subset of the reals contains an aleph-1 dense linear order by just throwing away the countable intervals. And therefore, in particular, any set of reals of cardinality aleph-1 is actually a minimal uncountable linear order. So in this model, any x subset of R, cardinality aleph-1, is a minimal non-sigma scattered now also, so definition, so a linear order L is Ehrenstein if it has no uncountable suborder which is separable or scattered. Now that's not maybe the usual way of defining it, but that's an equivalent way of defining it. So usually you would say it has no uncountable suborder which either contains a copy of omega 1 or is separable or contains a reverse of omega 1. But every uncountable scatter order contains either omega 1 or its reverse. So this is the same. And L is countryman if L is uncountable and L squared is a countable union of chains. And so if you look at the square, a chain is simply you look at the totally ordered subset of the coordinate-wise order on the. So a chain looks like kind of like the graph of a monotone increasing function, except that you're allowed to have bits that are horizontal line segments and also vertical line segments. You're just not allowed to have points that are like strictly above and to the left of other points. The fact that there could be an uncountable linear order whose square is a union of countable many chains is a shocking thing at first. And it was, in fact, Countryman's contribution to the subject was to conjecture that they don't exist. Shalah, a few years later, proved that they did by sort of rather indirect means, just in ZFC. And Stavo later came up with a much more direct construction of a Countryman line, showed that actually they're quite easy to construct if you only know what you're doing. And that was actually the way he tells it, that was his main motivation for the minimal walks paper, that was to actually come up with a construction of a direct construction of a Countryman line that was sort of more informative. Now, so I should say, it's not hard to show, and I think this was, I'm not sure who noticed this first, maybe it was Galvin or a number of people around the same time. Notice that every Countryman line is in fact Ehrenstein. It was only, so let me, don't want to get ahead of myself, let me just sort of carve out our board here and note, well, theorem of Abraham Shalah, 1985. that PFA implies every countryman line is minimal, and there are exactly two isomorphism classes of normal countryman lines. So normal is a somewhat of a strengthening of saying that it has its aleph 1 nets at every order, every interval is of size aleph 1. If you know what a non-stationary countryman line is, this is exactly saying it's non-stationary aleph 1 nets. And namely, you take any normal countryman line and you turn it backwards. Notice that if you take a countryman line and you were to take the reverse of C, and you look at the product, any uncountable linear order which embeds, any linear order which embeds into both C and minus C would give you a strictly decreasing function from C to C, like a strictly decreasing partial function, which would have to meet each of these chains in a single loop. And therefore, no uncountable linear order embeds into both a countryman line and its reverse. So you can't have, in particular, C is not isomorphic to its reverse. They're kind of non-reversible. They prove that, in some sense, this is sharp. That is, if you have PFA, every countryman line is minimal. It's not hard to show that just in ZFC, every countryman line is bi-embeddable with a normal countryman line. And then these normal countryman lines are sort of more or less phenomenal in the presence of PFA. There are just two of them. And I guess the point with both of these results is that they tell you that in the presence of some assumption like PFA, you have Labor's result is not sharp. That is, you can go to a broader class, namely, you take the sigma scattered linear orders, and then this single uncountable set of reals of size aleph 1. This is a hereditary class because every suborder of this uncountable set of reals is either countable, in which case it's sigma scattered, or else it contains a copy of the original one, so it might as well be hereditary. And it's well found. Kind of trivially, it's well found. Abraham Shalal result says that you can add a countryman line to the picture too if you like. So this raises some interesting questions, right? Is it true that there are minimal uncountable linear orders in ZFC, right? Just forgetting about what I announced on the first one. Could you have, in ZFC, a countryman line which is minimal, or a set of reals which is minimal, which is uncountable? Okay, so I think what I will do is erase this, and just state that as a question. I don't know who asked that. This is the sort of thing where you might as well attribute this to Galvin, because he did ask me, he didn't answer many questions like this. And I'm sure he thought about this. So is it consistent omega 1 minus omega 1 are the only minimal So let's just think about this for a second. Suppose that you had a minimal uncountable n order, which were, the first question you might ask, is it separable? Okay, so if it's separable, then it's a set of reals. If it's not separable, then it doesn't contain any uncountable separable suborders. And since it's minimal, it can't contain omega 1 or the reverse of omega 1. And so therefore it would have to be Ehrenstein. So this is really asking, is it consistent that there are no minimal real types and there are no minimal Ehrenstein types? Okay, so the no minimal real types is kind of easy. It goes back a long time ago to Bishop and Miller. I think this is 1940. There is no minimal suborder of R of cardinality continuum. So it is, in fact, they prove much. I mean, there are a class of results of this sort that they're all obtained by a diagonalization argument of length continuum. And what you show is that every suborder of R contains a very rigid suborder of R. And in particular, this very rigid suborder of R cannot embed into itself and so on. And this in particular implies that there are no minimal suborders of R cardinality continuum. So in particular, so CH implies no minimal real types. So notice that this kind of suggests that, so models of CH are perhaps useful for this question, the above question. I guess it's also maybe worth pointing out that every uncountable separable order is not sigma scattered, and every Ehrenstein order is not sigma scattered. So if we were interested in the question of can Laver's result be sharp, we might first want to answer this question, right? Is there a counterexample? Is there a witness to Laver's result not being sharp, which is just a set of reals or Ehrenstein line? Okay, so if you start with a model of CH and your model is going to be a model of CH, you've at least ruled out the minimal real types. But what about the Ehrenstein types? So this is, I was able to resolve this issue. This is around 2000. I think this is 2008. It is consistent with CH that there are no minimal Ehrenstein. So I'll say a bit about what goes into this proof. There's kind of an interesting trick here, and this is the model is a model is one in which CH is combined with consequences PFA. Right? So you take certain consequences of PFA, you get them in a model of CH, and you actually show that because that consequence of PFA in the presence of CH rules out the existence of minimal Aaron lines. I'll say a bit more about that later. Are there any questions here? I mean, this is maybe a good place to sort of pause for a second.
Is there anything special about Sussman lines?
Yeah, there's another result there which kind of has an interesting history. So when you think about answering this question, if you're pointed to a model of CH, you might think, reasonably, that a stronger enumeration principle, like diamond or diamond plus, might actually allow you to construct inside any Ehrenstein type a suborder into which the Ehrenstein line doesn't embed. But Baumgartner plus some other people, which I forget who these people are, and I need to kind of quantify that in a second, qualify that in a second, proved that diamond plus implies there is a minimal Sussman line. Now, what is this strained attribution? So Baumgartner published a proof of this. It was discovered relatively recently that there was an error in Baumgartner's proof. The error was fixed. Daniel Sokup was one of the people who fixed it, and maybe it was just him. Maybe he had a collaborator. I can't recall. Daniel has a few results that are around this, and I don't remember whether this one is just due to him or do you know Ishban or? Okay. So I should say plus. Okay. And basically there's a lemma that Baumgartner uses which is just incorrect, but they showed how to kind of show that the same argument runs with the weakening of the lemma, and that the weakening of the lemma is true, and something along these lines. So they didn't, the proof is not completely different than Baumgartner's, but there was a non-trivial thing to fix. It wasn't like there were just some details missing from Baumgartner's argument. So I should pause here and say a few words about an example with the Baumgartner. So that it's reasonable to ask at this point, is there, if you have a non-sigma scattered linear order, does it contain either a real type or an Ehrenstein type? Right? Maybe those are the only interesting examples of non-sigma scattered linear orders from the point of view of a basis. Turns out that's not true, but from the point of view of studying minimal guys, it is kind of true. The Baumgartner showed, so let C alpha and S be such that S subset of the limit ordinals in omega 1 be stationary. And C alpha subset of alpha is an omega sequence cofinal of alpha. So if you take one of these guys and you lexicographically order it, this is non-sigma scattered. And moreover, if T subset of S is stationary and S minus T is stationary, then let's call this L sub s, then L sub s does not embed into L sub t. That is, in some sense, this linear order remembers this stationary set up to non-stationary equivalents. And if you properly thin out the stationary set, you get a suborder into which the original one doesn't embed. So this example is a fairly broad collection of examples. They all look similar of non-sigma scattered linear orders, but what they all have in common is that they're not minimal. And there's a kind of a very sort of simple reason why they're not minimal, is that you can always take a stationary set and split it into two proper stationary subsets.
And if it's not stationary, then it's sigma scattered.
And if it's non-stationary, then it's easy to show it's sigma scattered. Yeah. So this linear order has the interesting property that not only is it, so if S is non-stationary, it's not only true that it's sigma scattered, it's actually a countable union of well orders. So this example is one which the well orders are somehow very present inside this. Every uncountable suborder of this contains a copy of omega 1, even though it itself is not a countable union of well orders. So this is what we call, let's call this a Baumgartner type. And now I want to kind of just hide what was, like bring back this, I guess it's gone. No, it's still there. It's still there. It's just barely. Okay, so PFA applies to every non-sigma scattered linear order contains xc minus c or Baumgartner type or reverse where blah, blah, blah. So the only reasons why linear order would be non-sigma scattered under PFA plus is because it contains either a set of reals, it contains an Edersheim line, or it contains one of these guys or the reverse of one of these guys, and that's it. Now, I mean, there's something that I don't know the sort of topological content of all of this, but there's something about the smells of not being quite metrizable, but almost being metrizable, right? That something is, when the stationary set's thinned out enough to become non-stationary, everything becomes nice and metrizable. Okay. So this is, so the question then, after this result, was, can this be strengthened? A precursor to what I just erased is a theorem to myself and Tetsui Ishu. This is from at least around 2009. PFA plus implies that every minimal non-sigma scattered linear order is a real type or Edersheim type. And so meaning a set of reals or an Edersheim line. Now, the key point here is minimal. Now and I guess I should also add an earlier result, my own, that explains the relationship to Countryman lines. 2006, PFA implies every Edersheim line contains a Countryman suborder. So the consequence of this, and Baumgartner's result, is that under PFA there are 5 uncountable linear orders, such that every other uncountable linear order contains one of these 5. Namely, your favorite set of reals of size aleph 1, your favorite Countryman line, its reverse, omega 1, reverse of omega 1. And so this, if you complement this, combine these 2 results, under PFA plus, every minimal non-sigma scattered order is either a set of reals of size aleph 1, your favorite one, or your favorite Countryman line, or its reverse. And we know that under PFA plus, this result is sharp because both the set of reals of size aleph 1 is minimal and the Countryman type is minimal. Now, at the time this result was proved, though, it was known that the fragment of PFA plus that you needed at least looked like it might be consistent with CH. So if you could combine, and moreover, it looked like it was also compatible at the same time with the part of PFA that's used in this model. So notice that if you could combine this conclusion and that conclusion, you would have a model in which there are no minimal non-sigma scattered linear orders, right? Because in this case, there are no minimal real types or Ehrenstein types. And if you prove that the only minimal non-sigma scattered orders are real types and Ehrenstein types, then okay, kind of ruled them all out. And indeed, that's how it works. So do I go until 5 or do I go until 10 until 5? Or it's somewhat ambiguous.
Let's say go until 5.
Okay, until 5. So what I'd like to say now is there are kind of 2 things that I think would be, you can't go too deep into the details of all of this, but it's worth saying a little bit about the combinatorial statement that you use to leverage for proving this theorem. And also, there's a characterization of being non-sigma scattered, and also a characterization of when you contain either a real type or an Ehrenstein type, which is kind of very useful in this context, and I thought it surprising. So maybe I would just sort of spend the remaining time stating the combinatorial statement and explaining how that theorem works, and then also talking about this characterization. So consider the following statement. Okay, so fix C alpha in omega 1, let's say in limit omega 1, which is a lattice system. So a ladder system is, I had it before on the example, each of the C alpha is just a cofinal subset of alpha of order type omega, which, so U is a statement that if G is a function from lem omega 1 into, let's say, 2, then there is an F from omega 1 to 2 such that for every delta in lem omega 1, F restricted to C delta is mod finite constant and takes the constant value G delta. Okay, so sometimes you write 3 lines indicates that something is just taking a constant value. I don't mean that this function is literally this constant value. I mean that this function is constantly that value with finitely many exceptions. Right? So if you go high up enough on the ladder, you only see one value of the function, and that is whatever G delta is.
This is topology.
This is topology, right? This is, I'm not sure whether the thing that I'm about to write up is topology, but this is ladder system uniformization or some variant of it, kind of a simplification of it. And yeah, this has to do with normality, yeah. perfect normality, I guess, or normality, anyway. Yeah. Okay, so okay, so it's a theorem, and I think this is this is really, I think, due to Devlin, but the paper that it appears in is Devlin and Shalom. I think the idea is that Devlin came up with the proof that I'm about to mention, and then Shalom abstracted it into something much more general, which is known as weak diamond. And proved that U implies 2 to the alpha naught is equal to 2 to the alpha. And I don't want to say anything about the proof other than, but we can talk about this afterwards. It's a cute argument, and it really is at the core of the iteration theory for preserving that CH is true. Like if you're iterating forcings and trying to keep CH true, it's really important to understand why this is true, because this is an obstruction. There's a forcing which adds a G for a given F, or sorry, adds a F for a given G, which doesn't add a real, but it tells you you can't keep iterating it because you will start adding reals, because in particular.
So is the statement U that every ladder system can be uniformized? Or is the statement U that there is a single ladder system?
It doesn't really matter. I mean, you could think about this as U is relative to some fixed C.
You know what I mean?
This says if for any C, for any ladder system, if it's true that this is true, then 2 to the alpha naught.
I think you need it for all ladder systems.
You don't need it. You don't need for all ladder systems in order. You just need for one single ladder system, and you can uniformize. Yeah. Okay. So. How does this go? So there's a weakening A. So fix both T and Ehrenstein tree and C a lattice system. So I guess here I'm going to, A is just a statement for every T, for every C, something is true. You say that for all G from, now again, lem omega 1 to 2, there is a F from now U, which is a subset of T, uncountable, downward closed, into 2, such that for every, say, U in script U of height delta, so for every delta in lem omega 1, for every U and U of height delta, if you look at F of U restricted to alpha, this is equal to G of delta for all but finitely many alpha in C delta. Okay, so here a picture is helpful. You have this element U of height delta in the tree. There's a ladder here. So this coloring, this function f, which is defined on the tree, is in particular inducing a coloring on the ladder by just for each alpha in the ladder, you have an alpha predecessor of u. The function f has a value at that alpha predecessor, and this is saying just that with finitely many of those exceptions, you're equal to this g of delta. So, of course, there may be many different things on that level of the tree. They may have different errors. It's also the case that it's possible that there are some elements of T which have all of their predecessors being in U, but they are themselves not in U. And then we have no requirements about what the function does on their predecessors. There's no requirement like this. So, and that's actually the key, is that so A plus CH is consistent, but A plus, there is a minimal Ehrenstein line implies that 2 to the alpha naught is equal to 2 to the alpha 1. In other words, the minimality of the Ehrenstein line allows you to sort of predict which of, knowing just what the tree is up to delta, and knowing the embedding that you see of the whole tree into the subtree, it allows you to predict which things are getting continued, and that allows you to do the coding that proves that this is true. Right, so if you want to get a model of there are no minimal Ehrenstein lines, you just get a model of in which A is true and CH is true. Okay, so, and actually the model for the curious, the model in which there are no minimal non-sigma scattered orders is obtained by iterating the individual forcings that force A, just those forcings mixed with sigma closed forcings, sort of out to a supercompact, kind of letting the Labour diamond sequence pick which of these forcings you use and which sigma closed forcings you use. And you only iterate those, and in the end you get a model in which A is true and CH is true, and moreover some other things which ensure that. Okay, so the final section is characterizing non-sigma scattered. Okay, so just from a kind of a combinatorial point of view. So for let's define L as some linear order, which we'll assume has no isolated points. If you want to take a product with the rationals or something, that will get rid of your isolated points. It doesn't really change whether it's sigma scattered or not. So, and L hat is equal to the completion. If Z is if Z subset of L hat and X is in L, we say Z captures X if there is some little z in Z, which defines the same cut over Z intersected with L as excellence. So this little z is not the same as x, but it somehow mimics x. And we say gamma of L is all z in the countable subsets of L such that z does not capture some x in capital L. And the theorem is that this is due to say myself, which is that L is sigma scattered if and only if this gamma of L is non-stationary. Now, there's a natural notion of equivalence among stationary sets like this, and it turns out that this gamma, in Baumgartner's example, is exactly returning that stationary set to you, indexing the ladders. And in some sense, what this gamma is kind of an abstract version of that, an abstraction of that stationary set. Now, it's there's another thing that I would like to and it's okay. So it's gamma L contains club if L contains a real type or Ehrenstein type. But that doesn't quite tell the whole story, because the real type, I mean, it's also the case that if I took the Baumgartner line and I took all of the ladders for all the limit orbitals, that would also give me back a club, it turns out. But we say that definition, if M is an elementary submodel of H theta, say countable, for theta large enough, we say that X in L is external to M if there exists a club E subset of countable subsets of L in M such that no N in E intersected with M captures X. And you say that it's internal if the opposite thing happens over time. So X is internal to M if there exists a club E subset of countable subsets of L and M such that for every Z and E intersected with M, Z captures X. So theorem issue of myself is that L contains a real type or Ehrenstein type if and only if some X is external to some M, and actually once there's some X which is external to some M, then for any M there's an X which is external to it, and you get a lot of overspill. In Baumgartner's example, it's the opposite. Every element of the linear order is internal to every model. So it's kind of the dividing line, and the additional use of PFA and PFA plus is to really make it so that either you have lots of either there is some element which is external, or you can thin out the linear order so that every element is internal. And once you have that every element is internal, you can get this allows you to mimic this thinning out process that works for Baumgartner's example. And if you have a bit more PFA, then you can actually push it further to get a copy of a Baumgartner line inside, or the reverse of the Baumgartner line. Okay, so that's both a good place to stop because of the material being done, and not being done, but whatever, being at a good stopping place, and also because the time is stopped. in 10 years from now, I'll try to have a topological result for you.
Any questions for Justin?
Yeah.
This result here at the end, that's really, really nice. Do you think there's hope for a common pro characterization that splits containing a real type or containing an Einstein type even further?
Okay, so it's actually pretty easy to detect when you have a real type because you just have to find that countable dense set which separates enough points.
Yeah.
The thing that is so odd about this result, to me, is that you would not think that you have a simple, sort of non-splitting characterization of when you contain these two different types of linear orders. Right? Real types and Ehrenstein types are kind of rather different things. And the fact that you have this characterization of when you contain one type or the other one that doesn't seem to mention either one of them by name is rather, I think, kind of remarkable. Like, I would not have expected this. It just sort of stumbled across it, in part because I was playing around with this principal MRP, which is a consequence of PFA, and is useful in making things be sort of either internal or external in this sense. That's the kind of underlying, the thing that was not mentioned here, but is somehow very much behind the scenes. The combinatorial principle that you need with PFA to make this work is you have, say, a bunch of, say, closed subsets, say D alpha, alpha and S, where alpha is D alpha, subset of alpha is closed. And what you want to do is be able to thin out a stationary set to a stationary subset where the D alpha is coming from that stationary set are either all containing that stationary set intersecting with alpha or all disjoint from it. So it's like a Ramsey theoretic statement. And that's something which it follows from MRP. But you can, if you just add a colon subset of omega 1, you get that sort of thing happening for free. And that's why the sigma closed sets work.
Any other questions? All right, let's thank Justin again.